Okay, so in this video, we are going to introduce the concepts of a superposition. So the superposition principle says that when two waves interact, they're actually able to just pass right through each other. And they will interact with each other while they're in the same location, but then they can kind of continue on their way. So let me show you what I mean by that. So I'm going to start two waves, one on each end of this torsion oscillator. And I want you to watch what happens as these two waves meet in the middle. I'm going to give it a pulse. So what happened as these two waves, they traveled together and then they interacted, and actually right where they interacted, they made a bigger wave. They added up together. And then they kept going on their way. Try it one more time. See it? Try to get it calm again. One more time. So right here in the middle, they made a bigger wave right when they were interacting. But then after they were done interacting, they just continued on their way. You can also have a situation where waves interact and they don't constructively interfere. That's what I just showed you, with the waves constructively interfering with each other, where they interfere and make a bigger wave. They can destructively interfere. This one's a little harder for me to do, so it may or may not work. But I'm going to try and make a pulse here go up. So it's going to send a pulse that is traveling this way up, and a pulse here go down. And then when they meet in the middle, we have a wave that's up and a wave that's down, and they're going to cancel each other out. So just for an instant in time as they're passing through each other, it'll look like the two waves just disappeared. But then they'll continue on their way. So let's see if I can do this. I'm going to try it one more time. You might just have to believe me that it works. They certainly didn't constructively interfere right here in the middle when they met. So there was a moment in time when they were destructively interfering when they were passing together. We mentioned previously that sound waves are these longitudinal waves that oscillate in and out like this as the wave travels in a certain direction rather than being up and down. So a longitudinal wave, to remind you, is a wave that looks like this, right, where the wave travels, and the way that it happens is it squishes together. It creates compressions of air followed by expansions of air, and compressions of air and expansions of air. And that pulse travels through the air and actually vibrates your eardrum, and that's why you can hear sound. We would be able to hear these pulses if our ears could hear just a few hertz at a time, just a few cycles per second, because that's what this is doing, right? But we can't. Our ears aren't sensitive enough to be able to hear that, so they can't hear that, but we can hear sound. So what I have here is two speakers. So I have this speaker here and this speaker here, and they're going to be playing the same frequency of notes. So they're both going to be playing about 400 hertz. And the cool thing about a 400 hertz wave is it has a wavelength of about 1 meter. So a meter is about 3 feet. So about the distance from this speaker to that speaker there is the wavelength of this wave. So we can actually, with sound, we should be able to see where constructive and destructive interference are happening with the wave. So let me turn this on. It's a little annoying to hear, so I apologize for that. So I've got both of my speakers together, and now as I move these apart, I want you to listen for loud and soft undulations of the sound. Where it's loud, you'll hear, that's where the wave is constructively interfering with itself. So there's a wave coming out of here and a wave coming out of there. Where it's loud, we have constructive interference that's occurring at the location of the microphone of this computer. Where it sounds soft, that's where destructive interference is occurring. So. you listen to that, you could hear it's somewhat subtle, and it's actually different for me than it is for you because my ears are not at the same location as your microphone. So where I am hearing loud and soft is different than where you are hearing loud and soft. But that is another example of constructive and deconstructive interference. Okay, so let's start talking about this, which is superposition. So, there it is. Actually, I'm going to move that so that I can get to it better. Okay, so the demo that I just showed you is this thing right here. It takes a minute every time I switch back and forth. I think I am going to zoom out just a little bit on the screen too. Okay. So the demo that I just showed you with those two speakers is this loud and soft thing. So these two waves are passing through each other, and they have regions where, if you imagine this sort of being like a peak of a wave, and this being like the trough of a wave. And as this wave spreads out, right, there's going to be regions where peak meets peak. So if your ear is right there, then you hear a very loud sound. There's also going to be some regions where peak meets trough. So as this wave spreads out, and it's actually going to spread out and make circles as they spread out. This will be a region where it's a relatively quiet thing. And as we just showed, actually, the wavelength of waves is on the order of feet. So it is actually not true that the loudest place in a concert is right next to a speaker. There's locations between these two speakers where it's louder and where it's softer. So if you find yourself struggling to hear, sometimes you can make a difference just by shifting a couple of feet around, and maybe it'll make enough of a difference. Also, if it seems too loud, shifting a few feet might make a little bit of a difference as well. Okay, but the main point here, right, is that these things pass through each other undistorted, which is a pretty crazy thing if you think about it. That the waves are able to just like pass right through each other, and when they're done interacting with each other, they just continue on. And this is a sort of diagram of what I was trying to show you with the torsion wave oscillator, where you have these two waves, and as they are traveling toward each other, right when they interact, they continue to make a bigger wave. So this wave is the addition, what you get when you add these two waves together. But then this wave, it's interacting with this wave, and then after it passes through the wave, it continues to pass undisturbed. Okay, so on a pencil and paper, we can talk about this principle of superposition for waves that have different shapes. So as these two waves add together, right, they're going to approach each other, and they're both moving at 1 meter per second. So here's this. This must be a snapshot graph because we're talking about what the actual wave looks like. 1 second later, this thing is going to move 1 meter because it's moving 1 meter per second. So 1 second later, it will look like that. And 1 second later, this will look like that. And that's actually what is drawn for the next one. Okay. 1 second after that, well, now this guy is going to move to here. Right? It's moved 1 meter. And this is going to move to here. So actually, they're interacting and they look like this. Okay. So this wave down here is going to be added on top of what's that. So when they're interacting, it starts to look a little bit like a house. And then 1 second after that, I guess second after that, they look like this. And the second after that, they look like this. So why don't you give this one a try? This is harder than it looks. So pause it, try to get an answer, and then when you're ready, unpause it, and I'll go through it myself. Okay, so here we go. Well, let's show the answer first. Oop, wrong piece of paper. So the answer here is A. So it looks like this. So let's try to figure out if we can determine why that must be true. Okay. So here is my, well, maybe I can just do this on here. 1 meter per second, and we want to know what it looks like at 2 seconds. So after 1 second, this is going to be from 2 to 3, and then after 2 seconds, this will go from 4 up to 4. So this rectangle here has moved 2, 4, 6, 8, 10. It's no longer from 2 to 4. 2 seconds later, it will be from 4 to 6. And now this thing is no longer from 5 to 8. I'm going to subtract 2 off of this. So instead of this being 5, it will be 3. So it's going to go here. And instead of this being 8, it will be 6. So it's going to go here. Okay, so this is a little harder because we have destructive interference going on here. So let's think about what this looks like when we add them together. Okay, maybe if I give this a y-axis, we'll make this a little bit easier. So let's call this +1 and call this -1, just so that we can think about this rather than it being a graph as being a okay, so right, as this, we're going to add this together. There's only one thing here. So let's just start with this period between 3 and 4 seconds. It's pretty easy. There's only one wave, and it looks like that. So I'll go 3, 4, 5, 6. So it's going to look like that. Right. This region between 4 and 5 seconds is fairly easy, easy, a little harder, but easy if you think about it. Right. Here we are at +1. Down here we are at -1. And 1 minus 1 is 0. So right here, between 4 and 5 seconds, these two waves completely cancel each other out. So they're going to look like that. Okay, and now how do we think about this one? So we're going to go between, I need to relabel my numbers here. I was pretty careless in how I put this little line here. So between 5 and 6 seconds, right at 5, we have 1 and -1. So they cancel each other out. Okay, so we have right at 5, it's 0. And at 6, this wave down here below is down to 0, and this one is up to +1. So by 6 seconds, we need to be up here. Okay. Let's think about 5.5 seconds. So right halfway in between. Okay. So now this is 1, and this one's -0.5. So 1 minus 0.5 is just 0.5. So we're down here. And you can kind of fiddle through with all sorts of different dots here. You know, right here at 5 3/4 seconds, right? This is still 1, but this is only 1/4. So we should be up to 3/4. And you can kind of fill in where your dots are and convince yourself that the string has to look like that. All right, so that is what the string looks like. Okay, so there's no displacement here. The question is, does that mean that there's no energy there? The answer to that question is no. Okay, the energy doesn't disappear. It's just in a different form. So it's not potential energy right now, right? So potential energy is the ability to do damage. When I displace the string, I don't have a string here, but I have a spring here, right? When I displace this spring, it has potential to do damage, okay? So if I imagine this being my string, right, while something is displaced, there's potential to do damage. So there's no PE. Right here, there's more potential energy. Here's less. Now there's no PE. It must be all kinetic energy. Okay, so we still do have these two waves that are passing through each other. So there's velocity in these waves. So we do have kinetic energy, but we don't have any potential energy. Okay. So standing waves is when you get two waves that pass through each other, and the way that they pass through each other actually acts to look like a single wave. And I've shown a few of these standing waves actually on that torsion wave oscillator. And I want to show a little bit different way of this, so I don't have to go back and forth between the two videos so much, right here. So, right, what is going to go on here is that I have, oops, make sure I show you what I want you to see, is that I have two waves, the blue wave and the green wave. And so the blue wave and the green wave are going to be passing in opposite directions to each other. And the yellow wave is what you get when you add those two waves together. So you see that the blue wave and the green wave have started off in pretty much the same spot. And so the addition of those two together is twice as big as one of them alone. Okay. But now as this moves, I almost hit it. There we go. I've almost hit this spot now where they're passing through each other, and now the blue wave and the green wave are almost completely canceling each other out. So there's this moment where it looks like the yellow line is completely undisturbed. And now here's a spot where they're constructively interfering with each other in some spots, and they're deconstructively interfering with each other in other spots. And you can see as they pass together. And so when you have a standing wave, what you see is actually the yellow. So there's two waves passing through each other, but what you will see is the yellow. And if you watch that standing wave, you see why we call it a standing wave. No, that. It's because it looks like it's just a wave that's getting littler and bigger and then littler and bigger, but the location of the nodes and the antinodes hasn't changed. So the nodes here are the spots where the wave, where the displacement is 0, and the antinodes are the spots where the displacement is the maximum value. So let's try to get the torsion wave oscillator up so we can see this happening in real time. Move it a little bit closer. So what I can do here is send waves, so you can see what I'm doing, is I can send a wave here, and it just passes back and forth like that. But if I send waves on both sides, then you will see that the wave goes up and down like this. And these two waves are passing together, but they're making a standing wave pattern. It looks like nothing is moving. And actually, I don't need to be forcing this with both of my hands because I can make the wave interfere with itself. Because if I send a single pulse here, then it comes back. So I can make the wave going this way interfere with the wave going this way. So here's what I can do. So I've made a standing wave. So the two waves are interfering with each other, just like that. And if I force this at a different resonant frequency, then I can make a different standing wave. And I've shown you this before, but I'm going to do it again because it's so cool. All right. So hopefully a standing wave makes sense. Oh, and I wanted to show you nodes and antinodes, just so that we can talk about that. So a node is, you see how there's some spots, I can even put my finger right here, where, whoops, my multitasking skills are being tested here. So I want to get a wave, so I have to force it at the right frequency. And there's these spots where nothing is moving, okay? So we have these, and then there's these spots that are moving the most. I'm not doing the best job of forcing my wave, but there's the spots that are moving the most. So we have these nodes where nothing is moving, And we also have the antinodes that are moving up and down. Okay. I have two very friendly children waving out my window right now, playing hide and seek and knocking on the window. So if you hear that, that's what it is. Okay, so this is what we saw, right? Where they're constructively interfering, we see this big thing. Where they're deconstructively interfering, we see nothing. And when they're interfering with each other, we get this standing wave pattern where we have nodes where nothing is being displaced together with antinodes that look like that. Let's try to figure out the wavelength of the standing wave. So pause it and figure out what you think the answer is. And then when you're ready, unpause it and come back. And here we go. So here's the standing wave pattern. So if you messed this up, what you probably clicked was B, but C is the right answer. So, right, I told you, you have learned that the period of a wave is the time to complete, is the distance of one complete cycle. Let me say that again. The wavelength of the wave is the distance for one complete cycle. And so it really looks like the wavelength of the wave is going from here to here, right? Just this half-meter distance. But actually, our true standing waves, remember, these are waves that are interfering with each other. So I have one wave traveling to the right and another wave traveling to the left, and they're interfering with each other here. So actually, the full wavelength of the wave, a better color here, is this full portion here. Oh, geez. Not saying this very well. So that is obviously not the full wavelength of the wave. That's only a half a wavelength of the wave, because as it goes up, it now needs to go back down. And we can get to there, okay? So this seems like now this is the full wavelength of one wave, right? It starts in a trough and it ends in a trough. And we have 1 meter distance from here to here. Okay, so we'll circle that one. Okay, so another example of standing waves is how every single stringed instrument works. And for the next video, I'll get some videos out, but for now, we're just going to try to visualize this. So a standing wave can exist on a string only if its wavelength is a certain resonant value, right? So a wave that looks like this can go up and down and up and down and up and down, and that can be the lowest harmonic is what we call that. And if you've worked in stringed instruments, then or probably in any number of instruments, you know things about what harmonics are, though you may not sort of know them on this sort of a level. So the first harmonic is the one that looks like this, where it's just the wave going up and down. The next harmonic, the next resonant frequency that is available to the string is this one. The one after that is this one. So there is a relationship that tells us what kinds of wavelengths can exist on this string, and it is right here. So the wavelength of the nth harmonic right is lambda n. Similarly, the frequency of nth harmonic. And of course, frequency we measure in inverse seconds or hertz. And wavelength we measure in meters. Length is the length of the string. And N is the harmonic. Okay, so following up with that quick check that we just did, right? So for the n equals 1 first harmonic, the wavelength of this wave, well, this here is a half of a wavelength. So the full wavelength must be twice as long as the string. And that's exactly what this formula says. So lambda 1 is 2 times the length of the string divided by 1 for the n equals 1 mode, and that is 2L. Okay, that's where this formula comes from. You could make it up. You don't even need an equation sheet for it. If we want to figure out the frequency of that, because the ultimate goal of stringed instruments, right, is to make noise, right? So we need to figure out what is the frequency of that string. Well, this right here comes from the equation that we have seen before, which is that V is lambda F, right? We've used that equation before. So if I solve this equation for F, I end up with the frequency as V over lambda. And now I'm going to go ahead and put these ins in here so that I can distinguish sort of which wave I'm talking about. And I can solve to say that the frequency, every time you go up in a harmonic, goes up. Like if the first harmonic is 100 hertz, then the second harmonic is 2 times 100. That's 200 hertz. The third harmonic is 3 times 100. That's 300 hertz. So every time we go up in a harmonic, we add this sort of n times the number of harmonics. So I have a video that I wanted to show with somebody who has devices that I don't have. So let's get that up on the screen. And not you. And we're just going to watch this. It's about 4.5 minutes long.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up.
Okay, I was playing this at double time before I started streaming this, but I'll slow that down for you.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump rope. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 and 1/2 wavelengths. So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50.
And actually, I pause it just for a minute because I want you to listen. We haven't been able to hear anything, but 50 is getting into the range of human hearing. So actually, when he goes up into 50, you'll be able to hear that up and down motion because this up and down motion of the string is creating its own, it's generating a sound wave from it as well.
And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
Nope, we won't. We're doing that on our own. Okay, so, but I have a similar question. It will be the last example of this video, which is talking about identifying harmonics on the string. So I have a 2.5 meters wave vibrates as 100 hertz standing waves, and it's got nodes at 1 meter and 1.5 meters. And no points in between. We want to figure out which harmonic this is. What is the string's fundamental frequency? And what's the speed of the waves that are traveling on the string? Okay, so let's pause it, get started. I want you to draw what you know. And so I'm drawing, not just write what you know. Let's draw this out. Draw the wave. It's 2.5 meters. The string that's 2.5 meters long, and see if you can figure some of these things out. All right, if you've given it a shot, as our answer here, let's make a 2.5 meter long. So we'll go 1/2, 1, 1.5, 2, 2.5. So there's 1.0, 2.0, like that. Okay. So it's 2.5 meters long. And we've been told that it is 100 hertz. So I don't really know how to draw that here because I'm going to draw a snapshot graph, not a history graph. So I'm not going to have a way to identify frequency from this. So I'll just write that down. So we'll say that F is 100 hertz. And while we're here, let's think about sig figs in our answer. So that all 3 of these numbers are written with 3 sig figs. So in the end, we'll want 3 sig figs. And it said I have a node at 1 and 1.5 meters. So a node is the spot where there's no displacement. So I have a node here and a node here. Okay, and it says then there's no points in between those two. So what the string must look like is this. Right, so this part is oscillating up and down like you saw on that full screen camera along those lines. Okay, so we'll write down this 2.5 meters. That's the length of the string. So L is 2.50 meters. See if there's anything else that I know. I don't think I do. Okay, so let's pull out the equation sheet and see if we can figure any of this stuff out. So we are looking for harmonic, fundamental frequency. The fundamental frequency is the n equals 1. So that's the lowest harmonic. And the speed of the waves. Okay, so if our wave looks like this, then the first thing that is easy for me to determine is the wavelength of the wave. So if this is half, this looks like half of a wavelength, right? So the full wavelength must be this whole thing here, which goes from 1 meters to 2 meters. So it's a wavelength is 1.0 meters. And I'm going to go ahead and put like wavelength of question mark, wavelength of something is 1.0 meters, this thing that is drawn here. But I don't know which harmonic that is, so I'm not going to go ahead and put a subscript on that yet. But so here, let's fill this in the rest of the way. Our wave must be a standing wave that looks like this. And I'll put little dashed lines for the part of the standing wave. That's the other end of it. Okay, so that's what our standing wave looks like. And so, right, like at any given time, maybe the wave looks like this, or like this, just like we saw in the video, right? So, but it's going up and down. This is always where there's no displacement, and this location here is always where there's a maximum displacement. Okay, and let's just call this N. We'll give it a name. I don't want to have a question mark. If this is N, it has 100 meters, and we've also been told that the frequency that corresponds to this wavelength is also N. So we have 100 hertz here. Right, this frequency won't be the same for everything because frequency depends on the wavelength, right? So the frequency won't be the same. But actually, you can see from this equation that the velocity, the speed of the wave, is always the same. So we'll be able to solve for one single v, but all of the frequencies and wavelengths will be different. Okay, so let's return to this. Nope, not that. This. Right, this is what the n equals 1 node looks like. That's the fundamental, right? The fundamental or first harmonic. This is what the n equals 2 node looks like. See how it has 2 humps? The n equals 3 node looks like this. So we can figure out which node this is just by counting up how many humps. I have 1, 2, 3, 4, 5. Okay, so this is the 5th harmonic. So this, for n equals 5, that is not a 5. Let's draw a 5. I have that F5 is 100 hertz, and lambda 5 is 1.0 meters. Okay, so now we need to figure out which harmonic is this. We got it. That's n equals 5. Okay, so this is the 5th harmonic. Okay, what is the string's fundamental frequency? So this is asking what is F1. Well, let's come over here. I could see it just as easily on my equation sheet, but it would be smaller. I'm going to look at this one where it says Fn equals n times F1. Let's use that equation to figure this out. So we'll say that Fn equals n times F1. And we want this. And we know what the n equals 5 mode looks like. So we'll say that F5 is 100 hertz, is 5 times F1. I divide both sides by 5, and I see that F1 is 20, and I'll make that be 2 sig figs, or 3 sig figs, excuse me, because that's how many I wanted, like that. Okay, so that's the string's fundamental frequency. And what's the speed of the traveling waves on the string? Well, we have, I'll put this back up here, right, this equation here, right, that comes from here, which says that v is lambda times f. So we know things about the lambda equals, the n equals 1 node and also the n equals 5 mode. So let's try it both ways and see if we get a different answer. So we'll say that v is lambda 1 times f1. Lambda 1, the wavelength of the 1 mode, is twice the length of the string. We did that just now, right? So we had, here's the n equals 1 node, the wavelength of this, it would be twice as long as the string is, because this is only half of a wavelength. So 2L times F1, which is 5 meters, right? The string itself was 2.5 meters. So this is 5.0 times 20. 5 times 20 is 100 meters per second. Okay, so there's our answer. I'll put a little decimal spot on it and give it a box. That works. You could also say that the speed is lambda 5 times F5, since we know both of those. Lambda 5 was 1. F5 was 100. And that also gives me 100. Works anyway, as long as both of these subscripts are the same. Don't do lambda 1 times F5. That'll give you the wrong answer. Okay. Wow, a lot of piece of papers. All right, so let's summarize what we've done on waves thus far. Okay, so we started talking in these videos about oscillation. So this is any repetitive motion. It could be a heartbeat. It could be a spring bouncing up and down. The amplitude, which we call A, is this maximum displacement from the equilibrium position. Equilibrium is this 0 line right here. The period T is the time that it takes to complete one cycle. So we are looking here at, is it a snapshot graph or a history graph? It's a history graph because we're showing the motion of a particle with time. So this was T. If this was a history graph, this would be an X. And it could also characterize this by its frequency, F. And the relationship between F over F and T is this. Okay. So sinusoidal waves, so these are waves that are sines and cosines. So they're squiggly like this. Moves one wavelength in one period of time, and that means that it gives this relationship here, which, as I showed, is really just a different version of the fact that it says velocity is distance over time. Okay, so this is the version that's written on your equation sheet. You could just as easily put a period in here instead of a frequency if you use the fact that you know that frequency is 1 over period. And in sinusoidal waves travel, every point in the medium is moving up and down with simple harmonic motion. So if you remember, simple harmonic motion is any kind of motion that looks like this. So hopefully you've all been staring at your microwaves since you watched that first video on waves, to get a good feel for what sinusoidal motion looks like, where the maximum speed is right here in the middle, and it has 0 velocity at the top and at the bottom. It's this energy sloshing back and forth between kinetic and potential and kinetic and potential. And we spent some time going through the difference between a snapshot graph here and a history graph to show that, like, the motion of a point, of like a chunk of string here, may look the same in the way that it's graphed, but it's sort of fundamentally a different thing when we look at our snapshot graph. So this would be the motion of a chunk of string as it goes up and down as a wave passes through it. Whereas this is what we would get if we just took a camera and took a photo of what the wave looked like in a certain time. Another thing, frequency versus period. So simple harmonic motion occurs when there is a restoring force that acts to return the system to equilibrium. So the spring is a perfect example of that. Right? As it is stretched, there is a force that wants to send it back to its equilibrium position. A pendulum is another perfect example of that. So here's my pendulum. And as I move this way, right, there is actually 2 forces acting on this guy, a tension force in the string and the gravity force. And both of those add together to want to make the pendulum move that way when I let go of it. And we have some relationships that describe how the frequency depends for a spring on the stiffness of the spring and also the mass of the spring. And for a pendulum, the frequency of that oscillation depends on gravity and also the length of the string. They don't depend on, neither of these equations depend on amplitude or the shape of the wave or any sort of things along those lines. This one does depend on the mass. The pendulum does not depend on the mass. So the 300-pound linebacker has the same frequency on the swing set as a 30-pound kid. We also talked about energy in simple harmonic motion, right? So where it passes through this equilibrium position, the energy is all kinetic. And when it is at the maximum amplitudes of its oscillation, the energy is all potential. So there we go. So the energy is kinetic, right? There's kinetic plus potential. So if we know the maximum speed of this, right, when it's here and it's all kinetic, then we can say the total energy is just 1/2 mv times v squared, where this is the maximum. If we know the period, the amplitude of the oscillation, then instead we can say that the energy is equal to 1/2 kx squared, where instead of this is the instead of putting an x here, we'll put the total amplitude of the wave. We also talked about damped harmonic motion. So this is oscillations that run down and stop. And we talked about underdamping. This would be something that is underdamped. We talked about critical damping, which is where it would just travel straight down and never oscillate. And then overdamped, which is also where it doesn't oscillate, but it takes a really long time to do that. Talked about resonance. Geez, it's been a lot of things. As being the system that has every oscillator has natural frequency or frequencies that it wants to oscillate at. And so resonance is what occurs when we have a large amplitude response to a pretty small amplitude forcing. So I gave the example of pushing on a swing, where you can push just a little bit, but as long as you're pushing just a little bit every time that person comes back, as long as you're pushing at the right time, then you'll eventually be traveling really quickly. All right, what about when waves travel? So in a transverse wave, the wave is going up and down. Wow, that's really loud. Turn your cell phone off. Okay, in a transverse wave, the motion of the chunks of string are going up and down, so they're perpendicular to the motion of the wave. In a longitudinal wave, the motion of the particles is going left and right, so it's in the same sense as the speed of the wave. But a sort of take-home point is that waves transfer energy, not matter. And actually, our sun emits waves. That's how energy gets from us to the sun. It can travel through a vacuum. It doesn't need to exist in a medium, because waves can transmit energy without having to transmit matter. Geez, we'll keep going. So waves require, mechanical waves are waves that require a medium. So this is a sound wave, right? No one can hear you scream in space is part of every single outer space horror movie ever known, and it's true, right? So the speed of that wave will be a property of the medium, okay? It's not a property of the wave. So this is, right, if this pulse is a little pulse, or this pulse is a big pulse, or this pulse is shaped like a funny looking fire, it doesn't matter. The speed of the wave is determined only by how tight that string is and how that mass density, how thick that string is. So for a sound wave, the medium that is required is the air particles that are compressing and expanding and compressing and expanding as that wave passes through. We also talked about the principle of superposition. So this is the idea that waves can pass through each other. And at the moment that they're in the same location, they interfere with each other, either constructively to be bigger or destructively to cancel each other out. But then after they have continued passing through each other, they will just continue on their way as though they would never interfered with each other in the first place. And we talked about interference. Jeez. Look at all these things. So superposition of two or more waves into a single wave is called interference. So, and I did this as a demo where I had two waves that were in phase with each other. They would add together to make it loud. When two waves were out of phase with each other, so they were just happened to be lined up so that they destructively interfered with each other, then when you add them together, it was soft. And standing waves were the two identical waves that were traveling in opposite directions. They can create a standing wave. And The spacing of the nodes are these spots where there's no motion, and the antinodes are the spots where there's the maximum motion. There we go with that. And I think we're finally done. The next video, we will start applying some of these principles of waves that we've gotten to sound. So I will see you next time.